Welcome back. In this video, we are continuing process sequencing, schedule design, and demand impact. I'm Beliz, and let's start it. We will introduce methods for sequencing, operation, and understanding production flow. Key charting techniques are assembly charts, flow process charts, precedence diagram help us visualize how parts come together and move through the factory. An assembly chart shows how components are combined to find a product. You start with the finished product and work backwards, disassembling into sub-assemblies and individual parts. This makes the assembly sequence more clear. While root sheet details each operation and assembly chart shows part relationship, the operation process chart gives holistic view. It root sheets onto the assembly chart. Standard samples represent operation, transport, delay, storage, and inspection. Here's two-handed process chart for cutting glass tubes. It tracks every left hand and right hand motion, useful for ergonomics and cycle time reduction. The summary table shows present versus proposed method, and the workplace layout diagram helps us redesign the efficiency. The precedence diagram interprets charts as network representation. They are more general than assembly charts. Think of critical path method or PERT charts used in project planning. These directed network establish a clear precedence relationship between tasks. Unlike assembly charts, which often follow a single disassembly order, precedence diagram let you explore multiple sequencing alternatives. Here's an example with activity A, B, C, D, and F. Each with early start, early finish, late start, late finish, and flag. This is how we schedule complex project or production lines. Now we move to schedule design. Before we can plan a facility layout, we need three inputs: marketing, the feature demand, the process requirements, and the schedule design itself. These three feed into each other. Marketing gives feature demand information. Pareto help us focus on the vital few products. Process requirements determine quantities. We need to know how many products are demanded, total production quantity required, machines and employees, the sequence of operations and inter-department relationship. We have three key questions: how much to produce, that's lot sizing; when to produce, that is scheduling; how long to produce, that depends on the marketing forecast. Schedule design impact machine selection, number of machine shifts, employee space, storage equipment, material handling, unit load design, and even building sizing. The volume, trends, and predictability of future demand heavily influence facility. A factory making 10,000 units per month for 10 years looks very different from one with the seasonal or seasonal demand. The image here suggests price sensitivity and demand elasticity, also critical for sizing the facility. Here's the key principle: less specific information leads to general purpose flexible facilities. Higher specific inputs from product, process, and schedule design let us optimize the facility. Optimized facilities are more efficient but less adaptable. It's a trade-off. This is the Pareto principle, often says like 80 to 20, but there we take it as a 85 of outcomes from 15% of the casus applies directly. A Pareto chart volume variety curve help us focus facility design on the vital few. high-volume product while handling the useful many low-volume items separately, perhaps with different styles or flexible equipment. Process requirement demand for calculations. Production requirement with scrap, with rework, the reject allowance problem, and finally determining the number of machine needs. Quantity determination is crucial for resource allocation. We must estimate scrap and solve the reject allowance problem, especially when effects occur randomly and cost of scrap is high. Scrap estimation tells us how many defective units we will likely to produce. This is essential for high volume production. Scrap comes from geometric waste or quality failures. The reject allowance problem concerns low volume production where reject happen randomly. If we need 10 good units, how many should we start with? It's a statistical calculation of using binomial or Poisson model to ensure we meet demand without massive overproduction. That wraps up our look at process sequencing, schedule design, and demand impact. These tools, assembly charts, precedence diagram, Pareto analysis, scrap and reject calculation directly shape the physical facility. Thank you for watching.